Hello everyone and welcome to this new session of hands-on deep learning using MatConvNet. So in this session I'm gonna be talking about how to create IMDb, so image databases, to do training and validation in MatConvNet. We're gonna be dealing with normalization of the data, and also we will address questions as what's happening when the dataset you're using doesn't fit in memory. Basically, we're gonna focus on the getBatch function. Okay. In a second part, we will be talking about fine tuning. So that means using a pre-trained network as initialization, and then specialize the network in our own new dataset. Okay. So for this session, I have created a small image dataset, a binary dataset containing small images from CFAR10. We have cat as the positive class. Okay. The most predominant figure on the internet. And then for the negative classes, we have the remaining classes of CFAR10, so horses, boats, cars, and so on. Okay. So the idea is to use this folder full of images to show how to create an IMDb, image database structure. That it is one of the main ingredients for using MatConvNet. So if we follow the session script first, and the usual thing already is to call VL setupNN to set up all the paths, and then we're gonna see this script I have created called create IMDb RAM. So we can run it first. We are just passing through the location of the folder with the images, and we get an IMDb structure with its typical structure, like containing the images, data, labels, and so on. Notice I have divided by 255 just because data is of type single, but we're using numbers from 0 to 2.5 in the range of the structure. So in order to let MATLAB know the sort of visualization it has to do, we need to divide by 255. It's just a matter of performing a good visualization with MATLAB. In any case, so let's go to have a look to this function create IMDb RAM. So this function receives a folder, so a path to the folder containing all the images, and it's gonna produce the IMDb structure. The IMDb structure is a MATLAB structure with several fields. That are the main ones are like images, which is another structure, and meta. Meta contains like metadata used for statistics and visualization. For instance, the name of the different classes of that dataset, or the names of the sets. For example, we have training set, validation set, and testing set, or we have different domains, like domain 1 is virtual, domain 2 is real, and so on. So this one contains the name for the domains, just to simplify things. And then you can add as many fields as you want. So we create the structure. Okay. And now we are gonna start reading images from the folders. So Here we know that the positive samples are in a subfolder called cat, and the negative samples are in a subfolder called no cat. All of them are JPEG images. We take one of the images as a reference just to know the height and the width and the number of channels of the images to perform some initialization now. Okay. We take the total number of images, summing both positive and negative images, and we start initializing fields like the metadata. Like we know that we're gonna have just train and validation images in this case, and the classes are no cat and cat. I'm gonna be using a label 1 for no cat and label 2 for cat. I skip label 0 because for the standard loss functions used in MatConvNet, 0 usually means like that you shouldn't take that instance into account. Okay, that's why I'm skipping 0. So yeah, we can start doing the initialization of the structure images. Images contains basically 4 fields. The first one is data, which are the actual data, so the images, the array of images. We initialize it to zeros. It's very important to notice that the data is a single. That's very important when you're using GPU. But also for CPU is gonna give you a nice speed up and reduction of memory. Then data mean is gonna be like the mean of all the training images, this data set. So that will allow us to later on do some normalization. And this is quite common in machine learning. And labels are the labels of each of the images. As I said, I'm gonna be using 1 for no cat and 2 for cat. And then set is a vector indicating for each image which set is belonging to, for example, training or validation. So in this case, it's gonna be 1 and 2. Okay, so far so good. Then I have a loop just to actually load the images and convert them to single. Okay. I assigned the label. In this case, I'm loading all the positives together, so I'm assigning label 2. Here I decide if they are gonna be part of the training or of the validation set. Yeah, I use like random number. Yeah, I'm gonna try to divide it like 60-40. 60% of the images are gonna go to validation and 40 to training. Okay, I think so far it's quite simple. Then I do pretty much the same for the negative samples. Okay, changing the labels and so on. Notice that during the loops I have been summing images and counting how many images have been used for training, and that's because later on I want to compute the mean. So I have been summing the images here, and then I can divide them by the number of images just to get the final mean. And later on we can use it to perform some normalization, so 0 mean of the data set and so on. Okay, now something that I consider quite important, a good practice, is to perform some randomization of the final images. So right now we have a stack of positive samples all together and then a stack of negative samples. So what we're gonna do is just to do some random permutation with the total number of images, and permute all the images, labels, and set consistently. Okay, and finally we just have to assign this meta structure and image structure we have initialized to the IMDb fields, and that's it. So we have created an IMDb. Let's gonna have a look to what we're gonna be using right now for training, which is a version of AlexNet with batch normalization. Okay, batch normalization was explored last week, and now we're gonna be using it for this first example. We have modified AlexNet just to adapt it to this new dataset. since the data is binary, we have changed the classifier, so the output is 2 instead of 10, as in last session when we were using like cipher 10. Yeah, and what is important for this session is to consider this function, get batch disk and get batch. So get batch is the interface of MatConvNet with your data. So get batch is on charge of reading all the data and creating the batches. So with the IMDb we have just created, we can just select a subset of images according to what is specified in the batch field. The batch field is basically a vector with a number of indices. So for example, if we select that our batch size is 50, then here batch is going to be a vector of 50 indices randomly selected, and we're going to use that vector to actually grab the images and the labels and create a set array, okay, like this. So this is as simple as it looks when we can have all the images in memory, so our IMDb fits in memory. And the only thing we need to care about is basically to check if we are using GPU to move it to a GPU array, so to transfer the data to GPU. This is not going to be the case because we are performing CPU optimization, CPU training, but well, this step should be quite automatic in any case. So yeah, let's gonna have a look to how we can train AlexNet with our new created dataset. But before, let me show you something slightly important, which is how to save this dataset. Yeah, if you try to save this dataset without using this minus v7.3 option, it's probably not gonna allow you because MATLAB has some restrictions in the size of the data you can save, and also on the formats. So every time you create like a big chunk of data on IMDb, you should use this minus v7.3 option, okay? Otherwise you will end up having some problems. Okay, after this interruption, let me show you how we can use the new IMDb to train on AlexNet. Okay, we just pass the IMDb, we select a name for the experiment. We are using Xavier's chloride initialization as in last session. Well, the training has started as usual. We see the dataset is not too big, like 8 mini batches of 50 images for training and 11 mini batches of 50 images for validation. So yeah, it's easy to handle for a CPU, although this is just, of course, a toy dataset. So, but the same principles apply for creating larger datasets up to some up to some size, like using 1,000 or tens of thousands of images. Okay. Later on I will explain what to do when we go beyond like the tens of thousands of images, and of course we don't have enough RAM in our system to deal with that. So we need to approach the problem in a different way. Okay. Now let me show you some basics about normalization. So after creating the IMDb, we can run this function I created to perform some normalization of the data. So now you have a look to the data. you will see that it's pretty different from before. Remember that I have to divide by 255 because in this case the range of the images are different. But yeah, you can see that colors have changed. Okay, and now we're gonna see why. So basically, this is quite common in machine learning, so probably you already know about this. But it's quite standard to take your data and shift it around 0. Okay, because that sort of improves optimization, so that's improving the training procedure. And in order to do that, we have computed the mean, the average of the image per channel for the training images we were creating the IMDb. And now within this script we can use that in order to subtract the mean to each of the images. Then some people also like to renormalize the values in a range that ranges from minus 128 to 128. Some other people use it from minus 1 to 1, or some other constants. I have noticed different improvements when using different methods of normalization, but typically when you're using batch normalization, these effects are not so critical. You don't see much change, but it's important to know that if you're using, for example, pre-trained models to do fine-tuning, as we're gonna do later, it's important that the new dataset you are creating is compatible with what the pre-trained network is expecting. So if the pre-trained network has been trained using a specific normalization, it's normal to normalize your data accordingly in order to match that normalization and make everything work reasonably well. It's also true that many times you don't need to do it, and you can start the training. At the beginning it's gonna be quite crappy, but the more iteration you leave it, the better it's gonna get, and things are gonna be working quite well without performing that sort of normalization. But it's always better to do it because, well, it's painless and it can give you quite a lot of improvement at the beginning in the initial iterations. So yeah, this piece of code here is just to rescale the range and that's it. Sorry, there is nothing else to say about this piece of code to perform zero mean and rescaling of the magnitudes of the images. So it's pretty much what this is. So now we can use the new generated IMDb. MatConvNet. If you run this second experiment, you compare it against the first one, what you will notice is that the network starts converging faster, a bit faster. Okay, so the error goes down a little bit faster, but at some point both configurations reach the same point and sort of move at the same speed. We also have to take into account that we are using batch normalization, as we just mentioned it. So what that means is the batch normalization is already helping us a lot. So here we can say, well, here we can see that in any case batch normalization is our first layer, and it's gonna be normalizing all the data. So in this case, in this sort of network, the normalization is not that critical, but it's gonna be important for next experiments. and when we have networks that don't use batch normalization or don't have batch normalization as the input layer, which is not always convenient, because sometimes batch normalization might introduce some complication during the training process. Well, sorry, during the validation process after we finish the training. So it's a bit tricky. But in any case, yeah, the data normalization is important and useful. Okay. Now, let me address the question: what happens when you have a dataset containing like tens of thousands of images or millions of images, and of course that doesn't fit in your memory? So, in order to deal with that case, I have created this second script called create IMDb disk. Okay, let's gonna run it. Now let's gonna have a look to it. So this script is pretty much the same as the previous script I saw to create the IMDb for RAM memory. It also includes an additional field called file names. So the file names are going to be a cell array of n cells, so one per image, and it's gonna be just containing the names, so where to find the images, so the path plus the names of the images. We are not gonna be initializing the images data to the correct size, because that will take us the whole memory in case we really have a large dataset. Of course, this is not the case, we are just using a toy dataset, but in case you have a really large dataset, this is the way you should proceed. So you avoid initializing the image data, and the one doing that will be your get batch function later on when training. So basically we construct this file name structure. Okay, we keep everything else the same, and that's it. Then, in order to perform training, we have to modify the get batch function. Okay. In this case, I have already created an appropriate get batch function to load images from disk. This is called get batch disk. And let me show you what is this function doing. So get batch disk is based on a method called imreadJPEG, which is a really optimized function to load JPEGs from disk, like in parallel using several threads that you can specify. Yeah, you can also use prefetch, so you can do asynchronous fetching of the images with several of the options that this method has. Basically, that allows you to load a batch of images, like while you keep running your MATLAB code. Okay, so it creates a different thread to do all the loading of the images in the background while you keep doing things. That's quite convenient when you want to start like fetching the next mini batch while processing the current mini batch. So every time you reach the get batch function again, all the data is ready. So I recommend you to play with the options of imreadJPEG. You can see them here. If you go to the definition of the function. But so far, I'm gonna show you like the basic behavior of how to use like the basic functionalities of this function. So for that, one of the simplest things is just to select a number of threads. In this case, I have selected 3 for my laptop. Yeah. So again, we receive a vector of indices. from the training procedure, and we just have to load that data. So for that, we call imread JPEG with the file names, which is a CLRI of the images we want to read. imread JPEG is gonna load that in memory. So now we only have to to check the size of the images, okay, and assign them to a matrix. So for that, remember that, well, before we were performing the normalization of the data, doing zero means, subtracting the mean, but here, since we are loading like the original images from disk, we should perform this sort of adjustment, this sort of normalization every time we load a mini batch. So every time we load a new images, we have to perform the sort of normalization we desire for this training, and that's why here I'm subtracting the mean. That's different when you create your own MATLAB extractor and you know that you want to keep the images in a specific format. But of course, when you are using JPEGs from disk, you're not gonna modify the image forever, applying some normalization and then save them to disk. You keep the original images, and then when you load them, you perform the transformation. Okay, so this is the difference between the previous getpaths and these new getpaths that takes everything from disk. So yeah, quite simple but effective. So if we try it now, we see that it's pretty much the same. So my hard disk is not introducing any really high latency here. So the main bottleneck is still the network performing all the computation. So it's quite fast. Of course, in order to do, if you want to do training, for example, in ImageNet or really large databases, I would recommend you to put all your data like in a solid state hard disk. So that really improves efficiency dramatically when you perform training. You can save like 50% of your time doing something like that. Okay, so this is so far everything I wanted to tell you about how to create IMDb's for MATLAB and MatConvNet, how to perform very simple normalization. Of course, you can apply more sophisticated ways of normalizing data using spatial contrast normalization or local contrast normalization and so on, using some of the functionalities provided by MatConvNet. Okay, but this is the basic ones. This is so zero mean, yeah, rearrange of the data. If you want to know more, just please try to investigate by yourself. Yeah, that's it for this first part.